think of an example. Let's say, does correlation coefficient being equal to 0 imply independence? And can we think of examples to the contrary? Can we think of examples where you might have a correlation coefficient of 0, but you will have a dependence between the two variables? And the answer for that is actually fairly simple. One thing we need to keep in mind when we're talking about correlation coefficient, when we're talking about dependence or independence, what we're talking about is a linear dependence or independence. And this should give us a clue. So let's pick an example, right? Let's take a curve that looks like this. Let's take the equation y is equal to x squared. This is not a linear dependence, but what does it look like if we were to plot, say, 5 points? So let's take the following 5 points. We have -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4, right? So what do those points look like? We have -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. So we have a curve that actually looks like this. And there is no question. There's no question at this point that x and y are actually dependent, right? Because as x increases, y is going to decrease if x is greater than 0. Sorry, y is going to increase if x is greater than 0. Y is going to increase as x decreases if x is less than 0. That's a very clear dependence over here. However, in this case, if we just have these 5 points and we were to calculate the correlation coefficient, we would find that there is no linear relationship between them. The correlation coefficient would be equal to 0. So what this means is that if coefficient is positive or negative, there is a linear relationship. That is, they're dependent. But if coefficient is equal to 0, all that means is that there is no linear, and I triple underline that word, relationship. That doesn't mean that there can't be other relationships. Just something to keep in mind. So just remember that a coefficient of 0 just means that there's no linear relationship between x and y, but there could be quadratic relationships, there could be cubic relationships, there could be exponential relationships, anything else, just not linear. With that, let's go on. Let's tackle an example. As soon as the screen changes, yep, there we go. Calculate covariance and correlation for the following data set. So we have a set of points. We have x and y. We have 3, 6, 10, 12. And we have 8, 10, 12, and 14. We have the mean and the mean for x and y given to us over here. And we remember the formula for covariance. I mean, obviously the answer is on the slide, but let's take a little bit and kind of remember that formula. Struggling with that word there. Xi minus mu x, yi minus mu y, divided by n minus 1. And there are reasons we picked n minus 1. That's to get an unbiased estimate of the covariance, as we covered a little bit in the previous video. So in order to find the covariance of x and y, we just plug all of these quantities into the formula. So 3 minus 7.75 into 8 minus 11, 6 minus 7.75 into 10 minus 11, and so on, divided by 4 minus 1, which is equal to 3, and that gives us an answer of 10.33. So 10.33 is a good estimate for, like, it's a good indication to us that covariance doesn't really give us any information beyond the direction of the relationship. What does 10.33 really mean? Like, what does it mean in context? Does it mean anything at all? We don't know much about the, we don't know really whether 10.33 means that there's a strong relationship or a weak relationship, because it's just a number out of context, right? So we can't really tell how strong this relationship is just from this number alone. So let's go about calculating the correlation. We have the same 4 points. We're going to plug them in to this formula that we came across, and obviously it's complicated. So over here we have the numerator and the denominator separately. Let's rewrite the formula over here so that's more neatly written. Xi minus mu x into yi minus mu y divided by the square root of xi, sorry, let's do that again. Square root of sigma over I into xi minus mu x squared yi minus mu y squared. And this, if we were to compute it, gives us a correlation coefficient of 0.04. And that's a pretty low correlation coefficient. It implies a slight positive relationship, but one of the reasons it's so low is because we only have 4 points, and it turns out the number of different linear relationships you can come across for four points it's not the highest, let's say. So if we were to have 4 points, I mean, if we were to have more than 4 points, we'd probably see this number be a lot higher. But that said, for what we have, at least right now, we know that there is a positive relationship, and that's kind of indicated to us from the data that we see over here. So perfect, let's move on. With that, we come to the end of this video. Thank you for joining me, and hope to see you around in the next one. Until then.